Okay, this time let's try to look at the copper smelting and the converting processes. This slide shows you the flow sheet of the copper making process from the ore to the final cathode copper. Typically, the copper is in form of the chalcopyrite mineral CuFeS2 in nature, and this mineral have also a lot of the gangs simultaneously. So we have to collect the more copper-rich mineral through the so-called combination or flotation technique. And by using this kind of technique, we can make a copper-rich concentrate, and this concentrate going to the smelting process. Before this concentrate going to the smelting process, we do the so-called roasting process in the middle here at around the 600 degree to 700 degrees Celsius. And this process is designed to remove the moisture from the concentrate and also partially oxidizing the minerals, which can reduce the burden in the smelting process. And when it goes to the smelting process, the copper containing sulfide minerals is reacting with oxygen and some additional flux. And by doing so, you can remove the iron from the copper mineral in form of the slag, FeO, SiO2 slag typically, and then a lot of the sulfur can be also produced as SO2. However, the end of this smelting process is not the final liquid copper. It actually produced so-called matte, and matte is copper iron sulfide liquid phase. And this matte is typically containing about 60% of the copper, and then the rest of them is iron and the sulfur. And this goes to the next stage called the converting process. And converting process is typically carried out in two-stage process. In the first stage, we remove the iron further by injecting the oxygen and SiO2 again. And that actually produced the FeO, SiO2, so-called pyrite slag, and SO2 gas again. And then in the second stage, that the remaining matte, which containing about 80% of the copper and then about 20% of sulfur, go to the second stage of the converting process. And even in the second stage of the converting process, we are injecting the oxygen and small amount of flux to remove all the iron impurity and then remove the sulfur to make liquid copper. And that liquid copper is called the bleached copper because it containing a lot of the sulfur and the oxygen as impurity. So typically when you cool it down, it can make a blister inside of the liquid metals. So that's why we call it bleached copper. And then this bleached copper going to the refining process and so-called fire refining. And in this actually refining process, we try to remove the sulfur and the oxygen simultaneously by injecting the different kinds of the gas and the agent here. And then once you actually reduce those kinds of impurity material, you can make anode copper, which is about 99.9% grade. And then to produce the final cathode grade copper, you do the electro refining process. Now let me show you the database we can use in the copper making process in FactSage. So typically what we are actually choosing for the copper smelting process is the FT miscellaneous database, FT oxide database, and the packed PS database. As you know, there's a lot of the gases producing, so packed PS is definitely necessary. And then we are producing also slag and some other oxide solid phase during the process, so we need FT oxide. And then liquid copper and the matte and all the sulfide minerals is existing inside of this FT miscellaneous database. So one of the things you have to look at very carefully is the FT miscellaneous database, because in the FT miscellaneous database, we even have two kinds of the matte page prepared for you. And historically, we made the FT miscellaneous database for the copper smelting process. And so we had liquid matte database, and then liquid copper database. And then about 10 years ago, we developed a new matte database and the old sulfide mineral database, which is useful for the phase diagram calculation for the sulfide containing system. So that's why it is little bit actually the confusing sometimes. What kind of database, what kind of solution you have to use in the FT miscellaneous database. So this slide show you kind of the clear actually the idea how to select database depending on your application. So for example, if you want to do simply copper smelting process in the liquid stage. So for example, if you want to do copper smelting process and also converting process and the refining process itself, you can simply use these two solutions mainly from the FT miscellaneous database. The first one is liquid copper, and this containing copper, lead, iron, zinc, arsenic, nickel, gold, sulfur, and oxygen, and etc. So this is the mainly for the copper liquid phase. However, it containing also some other impurity phase, including sulfur and oxygen. And then the other important actually database we have to choose for the copper smelting and the converting process is liquid matte database, and that is called the MATT matte database. And this is liquid which containing sulfur as a main component, and then copper, iron, nickel, cobalt, lead, zinc, and arsenic as the additional element here. And so here, as you can see, clearly it says that do not use simultaneously with the MAT2 and the FES solution database. And that FES is shown here, and that MAT2 is explained here. Okay, so as I mentioned, if you are doing just the copper smelting and the converting process, I recommend you to use only this and these two solution database from FT miscellaneous, and select all the solid compound, and then select also the other two database like this for the calculation. Then you can have the more or less good calculation all the time. And this FES, actually the solid solution, is the FES liquid solution is very special solution. This is FES liquid, which is only valid at very high FES condition. And in the most of the copper smelting process, you don't see this kind of condition. So you can more or less neglect this solution database. And the other bunch of the solution database here is related to the phase diagram calculation of this system. So copper, nickel, chromium, cobalt, iron, nickel, chromium, cobalt, copper, sulfur system. We made a complete set of the database covering from the solid state to the liquid state. So liquid state is basically this MAT2 database, which containing from the metallic system to the sulfide system completely. Okay, and then we have the many different kinds of sulfide mineral shown in this actually multi-component system, and all of this one is those kinds of the sulfide mineral phase. Okay, so if you want to do the phase diagram calculation or within this system, or if you want to do the copper smelting calculation even only within this system, you can still use this MAT2 database and all the other ones simultaneously, because between this one, everything is consistent. However, this MAT2 and this MAT is not consistent to each other, so you have to be careful. So once again, in general, if you want to do the smelting and the converting calculation, I recommend to use these two. This is most simplest one, even including some other impurity you need in the industrial scale process. And this is good for the phase diagram calculation between the sulfide and the metallic system. And then you can even cool down this one, cool down the mat to calculate the separation of the sulfide and the metallic actually phase too. From now on, I'll show you briefly different process we want to calculate by using the phase. And the first one will be the roasting process, and second would be the smelting process, and the third one would be the converting process. Let me show you all this one through the presentation file first. and then we'll do the real calculation by using the fact age, by step. Okay, so the first actually the process is the roasting process. As I mentioned, we have comminution and floating process, and from that we actually make a concentrate, and this concentrated copper minerals can go to the roasting process at around 500 degree to the 700 degree Celsius. The main purpose of the roasting process is to partially oxidize the copper mineral to the oxide minerals. Okay, so the main target is the reducing some of our chalcopyrite to the iron oxide phase, and the remaining would be the sulfide phase. Okay, so this is the oxidation reaction. So it's extremely exothermic reaction too. So in the industry, we are using three kinds of the roasting furnace typically. The first one is the flash roaster, and then second one is the Hershey roaster, and the third one is fluidized roast. If you go to the copper company, sometimes there's the very big rotary kiln type of the furnace, and that is actually typically similar to this Hershey roast, and that is for the roasting process. So let's assume that we have the original mineral like this, and I'll add this one into in the fact phase. And after actually you're adding all this the species in the fact phase, you're going to select the three database, and fact PS, FT oxide, and FT miscellaneous database. And in this case, because we are actually talking about the low temperature mineralogy without actually the matte formation, so it is not involving any kind of liquid phase. So we're going to choose all the oxide database and all the packed PS database, and also we'll select all the FT miscellaneous database except for the FELQ, CULQ, and the matte and the FES, because this thing is only useful at the very high temperature when you have the liquid copper and the liquid matte is forming, and same for the FES. So we are going to remove this one, and we'll take the less of the sulfide mineral database, which is internally consistent to each other. Okay, so in order to simulate the roasting process, we are adding all the mineral like this, and then we are adding additional air, so 0.979 moles, A moles of the nitrogen, and 0.21 A moles of the oxygen. And whereas the A is actually the variable we can choose. And the A will be changed from 0 to 50 in every 1 at 600 degrees Celsius to see the result. Now these two graphs show you the calculated result. So the first graph is the amount of the different phases forming in this the roasting process with the increasing amount of the air in moles. The alpha is the air amount. So as you can see here, there's the copper sulfide kind of phase here, and then there's the pyrrhotite phase, and then there's the degenerate phase, which is the Cu2S rich phase. And then there's also spinel phase, which is Fe3O4. So the pyrrhotite, this one here, is the FeS rich phase. And as you can see in this calculation, the pyrrhotite is converted to the spinel phase, Fe3O4 phase, by reacting with the oxygen. And then once you pass the amount around the 11 or 12, actually the moles of the air, then you can start to also reduce the Cu2S phase, and then it starts to actually form the degenerate, and then further increasing the spinel phase. Okay, and now if you look at the right side of this diagram here, this shows you the energy balance. So as I showed you before, we use the initial condition for the initial minerals and the air at 25 degrees Celsius. So this delta H is the energy difference between the initial condition and the final condition at 500 degrees Celsius. Okay, so typically when the delta H is positive, it means it is endothermic reaction. So it means you have to inject this certain amount of energy to maintain your final temperature, 500 degrees Celsius, 600 degrees Celsius in this case, sorry. And then if it is negative value, that means it is exothermic reaction. So you have to take out this amount of the energy to maintain your final the temperature. So you have to cool down your furnace. Okay. Interestingly, if you look at this calculated result, when the alpha is about 10, the energy balance is become almost 0. Of course, in this calculation, we consider no heat loss, okay? But nevertheless, about the 10 moles of the air, you have energy balance 0, and also at 10 moles of the air, you can reduce the pyrrhotite, and then it has a spinel phase. So if you consider the purpose of the roasting process, that was removing all the moisture and also partially oxidizing our sulfide mineral to the oxide mineral. So you can say that the calculated result at about 10 would be the reasonable result for the roasting process, reasonable condition for the roasting process. Of course, you can target something else, but in this calculation, let's assume the amount 10, alpha equal to 10, is the target roasting process. Okay, so once you do that, then you can save all this the result from the result from the A equal to 10, alpha equal to 10 as input for the next calculation. Now, next step is the smelting process. As I mentioned before, the smelting process is designed to remove the certain amount of the iron from the concentrate and produce the liquid matte for the converting process. So this process is typically carried out around 1200 degrees Celsius, and because our original mineral, the roasting the product is still containing high amount of the iron and the copper sulfide. So we have to inject oxygen to remove some of this iron sulfide to the iron oxide, and then also we have to add additional agent like SiO2 to form the iron as iron silicate slag. By making this kind of iron silicate slag, we can reduce the activity of the iron oxide. So in that way, by doing so, we can make more easy chemical reaction for the conversion from the iron sulfide to the iron oxide, because the activity of the FeO in the slag is lower than 1. So the proper amount of the SiO2, the flux, is very important parameter to get the good smelting process. So once you finish this smelting process at around 1200 degrees Celsius, you are taking out this slag, and then you are tapping out this matte as a separate product, and then this matte is going to the next stage called the converting process. So we're going to simulate this smelting process in this way. So as I mentioned, we did the roasting process at 1600 degrees Celsius. And also I mentioned that A equal to about 10 is the good roasting product. So we recycle all the output of all the output at A equal to 10 as a stream file like this. So we have all this kind of stream, and 100 means we are taking 100 amount of the total amount of those product as it is. And then we took out, we want to remove the gas phase at least. So I set the gas amount as 0 and all the other one as 100%. And in order to also perform the energy balance calculation, I take the input temperature as it is. Okay, so initial condition, click the initial condition, and those temperature at 600 degrees Celsius, and with the energy is coming simultaneously. And then in the smelting process, we have to inject the two kinds of the material. One is SiO2 as a flux, and so I set it as a B beta, which is constant value I can set in the calculation. And then I inject the oxygen. And typically in the in the copper smelting process, people want to use the more high concentrated oxygen air. And so instead of using the normal air, I just make a special air called 0.36 moles of A, and then 0.64 moles of the A, actually the air. So it's a 36% oxygen enriched actually the air. Okay. So you actually set it in this way, and then you go to the next, then you actually can see this one. And now here, the database selection is very important. As I mentioned, we are now doing the smelting actually calculation. So it involves liquid metal or liquid matte. So in this case, the best actually the database we can choose from the FT miscellaneous database is the CULQ and the MET. So this one CULQ and the MET. And then we are taking all FT oxide solution, of course. And then we are taking all solid and all the gas phases. And then we set the temperature, and we set actually the flux amount, the P for the SiO2 as 10. And then we change the amount of the oxygen enriched air from 0 to 50 every one actually step. So the flux amount here is actually very critical, but I performed a couple of the calculation, and also I took some reference data from the industry, and I set 10. Okay, and then do the calculation. Then you get the result like this. So you can actually check one by one all these results, but I'll show you only the result when A equal to 16, and because this actually gives you the reasonable value already. So the end of this smelting process, the target is the matte grade about 60%. So it means I only have the copper content in the matte around the 60%, and that is actually the good for the next actually process, the converting process. Okay, so and also the other actually the important criteria for the smelting process is end of this process you have to produce only matte and the liquid slag, and because if you have some sort of the solid slag or some solid phase in the process, it is very difficult to actually the sound tapping. So it's difficult to remove the slag from the furnace. So it is worthwhile to actually sacrifice a little bit of the actually your matte grade to maintain everything as a liquid state. Okay. So this when alpha equal to 16, you can see that there's the gas phase, and gas is mainly N2 and SO2. SO2 is about 30%, and then you can see the matte, 500 gram of the matte, and then about 380 gram of the slag. And then if you check actually all the rest of species, all the rest of the phase, it's zero amount. So you have only liquid matte and the liquid slag is producing when you have the A equal to 16. And then if you look at actually matte grade here in here, the copper actual amount is about 58.9%. That's not exactly 60%, but this is good enough for our converting process. So we can take this matte as input for the converting process, for example. And this slide shows you the overview of all the results I calculated before. So the first plot is the change of the different phases with the amount of the oxygen we inject. So as you can see here, this is the matte, and this is gas phase, keep increasing, of course. And then here you have slag phase, and then this is phenol phase, as you can see. And I think this is the SiO2 itself. Okay, so here there's actually certain range between 10 to about 16. You can have only liquid slag and the liquid matte and the gas phase. And if you actually go above that, then you have spinel phase because you're injecting too much oxygen. So the oxygen reacting with the iron sulfide and it produces the spinel phase instead of the liquid slag. So Fe3O4 is start forming again. So this is solid phase, which is not good for the tapping. So the best one is from 10 to about 16. Okay. And then if you look at now the composition of your mat with actually oxygen, it looks like this. So this is the amount of the copper in the mat, and this is sulfur amount, and this is iron amount. Okay. So if you look at from 10 to about 16, the copper content is keep increasing, iron content is keep decreasing. Okay. And so you can actually see that 60% is about here, and that is reached at around 16. Okay, and this is now the delta H, the energy balance. So our initial input is the product from the roasting process at 600 degrees Celsius, and we are injecting additional air and SiO2 from the room temperature, and then we set the final temperature at 1200 degrees Celsius. And then this is the delta H difference between that initial and the final. With increasing amount of your air. So as you can see, this is 0, okay? So again, about this area, you'll have the endothermic reaction, but after this one, you'll have exothermic reaction. So when you see from the 10 to about 16, it is all negative value. So it means you have the exothermic reaction. And by the way, this is in kilojoule. So this is about couple of the 100 kilojoule. Actually, the energy is produced per around 500 gram of the input. Okay. And let's check again. Okay, so the matte is about 500 gram, and then slag is around 200 or 300 or 400 range. Okay, under that condition, your energy is about minus 500 kilojoule at when A equal to about 16. So it's exothermic reaction. So in order to actually maintain this temperature, you have to cool down your furnace by using for example, water cooling. Okay, so by comparing all these results, we can say that A equal to 16 is a reasonable actual value. Okay, and by the way, if you actually change the B, the SiO2 flux amount to 50 gram, you can actually produce the copper matte, which is close to the 61%. Okay, however, you're adding more flux first of all, and by adding more flux, you'll actually increase the burden for your furnace as well. So you have to actually think about what would be the good balance for you. Okay, and in this case, I'll take the B, the SiO2 flux amount as 10 gram, and then take A as the 16, and then we can save actually the matte from this calculation, and save it as a stream for the next calculation, the converting calculation. Okay, so this show you how to do all those saving. Okay, so at the 16, you go output and then stream file and save stream file, and then what phase we are saving is the matte. Okay, and then you can name it whatever you like. Okay, so next stage is the converting process. So in the converting process, what we want to do is we want to convert sulfide matte to the bleached copper, liquid copper. Okay, that's why we call it converting process. Okay, so this actually process is typically carried out so-called Pierce-Smith converter. Looks like this. So we have the kind of big mouth in the top here, and we have oxygen tier on the side, and then this is actually rotating furnace. Okay, so we are charging the mat here in the first, and then we tilt it back, and then put actually aligned with the hood, and then we are injecting the oxygen. Then the oxygen reacting with the sulfur and then produce SO2 gas, and it goes to the actually exhaust gas through the hood, and then a certain amount of oxygen reacting with the iron produce the iron oxide, and then that iron oxide is the reacting with the SiO2 plus to make a slag phase, of course. And then once our matte actually grade going to the about 80% of the copper, then we stopped actually the oxygen blowing, and then we are tapping out the slag, which is typically so-called the pyrite slag, Fe2 SiO4 slag, and then we tilt it back again, and then we are injecting the additional oxygen by adding little bit amount of flux again, and then we are producing the bleached copper. Okay, and that's two-stage process. So in order to simulate this two-stage process, we save the matte from our smelting process. So here, this shows you the first stage of the converting process, and that is basically removing the iron from the sulfide matte to the slag phase. Okay, so here we take that matte we produced from the smelting process, and we are injecting a certain amount of SiO2 flux, and then we are injecting also oxygen, 36% oxygen enriched actually the air here. And we set the B in this case as 50 gram, and then A we are changing from 0 to 10 and average 0.5 moles. Okay, and then the temperature is set as 1250 degrees Celsius. Even in this case, of course, the database selection is same as our smelting process. Okay, so once you do all the calculation, you can check all the result, and the best one I found was A equal to about 7. Okay, when A equal to 7, you can see that there's about 360 grams of the matte, and which containing 0.14% of iron, very small amount of iron, and then your copper is about 80%. Okay, and then you're producing about 168 grams of the slag, which is about 29% of SiO2, and then you can sum up FeO, Fe2, together. That will be about 55%, as you wish. And then there's the certain amount of copper oxide, about 6.8% of the copper oxide, CO2. In fact, this amount of copper oxide loss is a little bit too much for the economic actual process. So you have to watch out to this copper oxide amount. And this is a little bit too much, but we can take it as it is in this case. In reality, instead of adding only SiO2, we're adding some other actually the flux as well, like a CaO and the Al2O3 and etc. to adjust actually slag composition a little bit better. By doing so, you can actually reduce the actual copper oxide amount a little bit less. Okay, so let's take this A7 condition is the good condition for the first stage of the converting process in this actually the example. Okay, that it means we are going to save this matte for the next calculation. Okay, so we save that, and now we go to the second stage to making the bleached copper now. So we took that stream. We actually input the stream file of the matte, 80% matte we just made, and then we are also adding small amount of SiO2, and then also the nitrogen oxygen gas like this. And the amount of the SiO2 is extremely small because we have the very small amount of iron still remaining in our upgraded matte, and so in order to remove that, we need only very small amount of the SiO2, 0.3 gram in this case, and then we are changing the oxygen from the 0 to 10, average 0.5 mole at 1250 degrees Celsius. And then once we do the calculation, then we can see different result. But when A equal to about 6, and this is the result at 6, we can see that there's the liquid copper is produced now. Okay, and liquid copper, about 286 grams of liquid copper, it containing only about 0.53% of sulfur, and then about 0.15% of oxygen as impurity. Okay, and then the iron amount is 1.8 10 to the minus 3. So it's extremely low enough actually for the bleached copper, actually the condition. And that actually iron went to the slag by reacting with SiO2. So you see that there's the SiO2 and then some amount of the actual oxide, iron oxide. And then you're also losing certain amount of the copper as a Cu2O in the slag. So you have to watch out also this copper. And typically when you have the copper concentration higher than 1% in your slag, then you collect the slag and then recycling back, because this is actually the more than actually more higher concentrated actually the source of the copper than original mineral. So it's better to recycling back inside of actually smelting process. Okay, so we can assume that this is good enough actually the copper bleached we can produce. Okay, bleached copper. And then you can actually take this one and then go to the refining process if you like. So I'm not going to do the refining process calculation, but the basic concept of refining process is shown here. So we have the both sulfur and the oxygen impurity inside of bleached copper. So what you have to do is we have to remove the sulfur by injecting the additional oxygen, and then you're going to make SO2. And by doing so, actually, you are injecting a little bit too much. You need a lot of the oxygen to remove all the sulfur. And while you are doing that, certain amount of copper also reacting with oxygen to make a CO2O. So you have to watch this one very carefully. Okay. And then now sulfur is gone. However, there's too much oxygen can actually go into your copper. So we have to remove the oxygen. So removing oxygen is typically done by the addition of CH4 gas. And CH4 is reacting with oxygen or CO2O and make a CO2 and H2O gas. And in this way, you can remove the oxygen from the liquid copper. Then you can get actually the anode copper grade, which is 99.9% or more pure. And the sulfur and oxygen level can typically go into this range. Okay, and then this anode copper can be sold out as it is, or it can actually go to the electro refining process again. Okay, so this shows you the overview of the copper smelting process and how we can actually utilize the phase for the roasting, smelting, and the converting calculation. And now I'm going to show you the real calculation by using the phase. And we're going to look at step by step all this calculation actual process.